So, good afternoon and a very warm welcome to this Clean Aviation session. I think we are going to start. We can't wait for the late lunches. There's still people to come, but we have quite a busy agenda, and we need to be finished by 3:30 in order to prepare for the von Karman Award. I think I mentioned that this morning. This afternoon, Clean Sky 2 is going to receive, if all is true what I've heard, the von Karman Award, and there are going to be Sabine Klauke, the CTO of Airbus, Eric Dalbiez, the CTO of Safran, and also Marco Protti, the head of advanced research of Leonardo Aircraft, on stage in order to present to the audience their work in Clean Sky 2. So it's going to be a nice event, so that's why we have to be definitely finished by then so that the new crowd can come in. Clean aviation. I think we touched a bit on that for those of you who were here already this morning. We touched a bit on that already in the various presentations about Clean Sky, because Clean Aviation is the successor program to Clean Sky 2. And some of those elements which have been developed and to a certain extent matured in Clean Sky will be transferred into Clean Aviation, will be further matured and will be then demonstrated at ground test or flight test level. So what we are going to try this afternoon is to give you an overview about the Clean Aviation program, the rationale, and then also focus a bit on the three big thrusts which we have defined. You will see that in a minute by the presentation of the different speakers. So ultra-efficient aircraft concepts and engine concepts for short medium range aircraft, hybrid electric regional aircraft concepts, and also the technologies for the use of hydrogen on board of regional, respectively, also short medium range aircraft. So that's going to be the focus of the afternoon. And in terms of program milestones, we have been receiving lots of proposals for the first call, which has been put out there up to the end of June. We are currently in the evaluation process of the different proposals, and by the end of this month, we should have a decision which proposals have finally succeeded and can then be starting with the technical work towards the end of the year. So that's the overall milestone, but I'm sure Ron is going to tell you a bit more about it. So the first speaker, Ron Vanmanen. Ron is providing, as I indicated, the overview of the program in order to set the scene. And Ron, in terms of background, has held various management positions in airlines, in KLM and also in British Airways. Before, in 2003, he joined Kinetic. So he became the managing director of the aerospace consulting division in 2008 and held that position until he finally joined Clean Aviation, the joint undertaking, in 2011. He became program manager for the program in 2014, and since 2019 he is head of strategic development, which is the organization which has prepared all the work and all the work coordinated which is relevant and focused on the Clean Aviation program. So, Ron, please, over to you.
Thank you, Axel. It's wonderful to be back in Stockholm. It's great to see this community back together again at ICAS 2022, back from an intermezzo, which I think we all are very keen to put behind us in terms of the years of the pandemic. I'll show you a slide you've seen in a relatively similar way earlier. Frank Haselbach showed one, but based on the so-called certification dates of either engines or aircraft. And there's a really nice trend in terms of the improved efficiency. This, however, actually looks at the installed base, or the fleet in service, and there are a couple of lessons we can draw from that, and I'll return to that at the very end. Data, by the way, is open science, so I'm quoting freely here from what, in terms of origin, came from Manchester Metropolitan University and the faculty surrounding Professor David Lee. If you look at it from 1969 to 2019, and for me, 1969 is relevant in many dimensions. First of all, that's when I fell in love with the aviation industry. It's when the 747 entered into service, the dawn of mass travel, And it was a period in which my father was the chief engineer of the Apollo program and of the Concorde fuel system. So I was reading Aviation Week at the age of 8, which I wouldn't recommend to my children, but it kind of happened to me. 69 to 2019, 50 years. Why 2019? It's kind of the apex of the aviation system pre-COVID, so it's a relevant year, and 2020 much less so. Actually, in the installed base, we've seen an 80% improvement in fuel efficiency and energy efficiency. I don't know of any other sector that can compare to that. 1989 to 2019, 30-year period, but that also is looking at the other exponential lines that you see here. Quadrupling of the aviation system in volume, and a doubling of emissions, by the way, by that. And we've, I think, for a decade or two, been able to say that that's good performance, and it was good performance, but it's not enough. If we're looking at a climate-neutral future, it won't suffice. So we know what we need to do. But where do we start? And how do we do it? There's an old saying that says when you're looking at numbers, there are such things as lies, damn lies, and statistics. I like this graph because it shows, and this is data, International Council on Clean Transport, the ICCT, and it tells us, I think, where we can find let's say, the next steps. So where do we go first? And I think it's very revealing. You'll hear very often that 80+% of the aviation system transport people or goods over lengths or over distances for which there is no alternative mode of transport. It's probably true. But you'll hear it morphed into the statement you often hear that 80% of aviation is long haul. That's absolutely not true. Or that 80% of aviation's emissions are long haul. That's equally not true. Now, it depends on how you define long haul. If I'm in my car, long haul for me is kind of beyond Amsterdam, Brussels, because it gets annoying to travel further. If I'm traveling by rail, I don't mind Amsterdam, Paris, or Brussels, Lyon, but then it gets a bit annoying. I think the consensus in aviation is that long haul is transcontinental as a minimum, maybe even intercontinental. And this chart is enormously informative because 1/3 of aviation's emissions are on flights below 1,500 kilometers. A further 1/3 of those emissions are on flights subsequently up to 4,000 kilometers. And only 1/3 are actually on flights that take place that have a sector length of over 4,000 kilometers. And the trend, if you look at 2050, there have been numerous scenario studies in this, actually points towards a further concentration in the short, medium range environment. And that's important for us. Now, I know you could take the political line, we just stop flying over short sectors. And I would say dream on. If you look at the number of city pairs that aviation can touch and the efficiency of doing so, and doing so profitably, and doing so without massive infrastructure investment and massive life cycle effects of that infrastructure, short-haul aviation will not disappear. You can also look at it in another way, cumulatively. Here I've overlaid the fuel with the actual cumulative number of flights over the different segments, up to 500 kilometers, 1,000, and subsequently. Same ICCT data. The overlay comes from the Sabre computer reservation system, manipulated with our thanks by DLR, the German Aerospace Center. A couple of things are pretty interesting. Only 1% of flights are over 8,000 kilometers in length. We design long-range aircraft for 8,000 nautical miles. Ultra-long haul is therefore an even more marginal market if you're actually looking at city pairs. It used to be the case that flights over 8,000 kilometers consumed roughly 20% of fuel. But I think, again, it's a recognition of the performance of the sector that if you now look at the so-called big twins, the A350, the Dreamliner, the 787, it's actually a bit less. It's towards 15%. But it underscores where the first big steps are needed. Again, another way of looking at this. So I've complicated the slide by looking at that. How can we move forward? One thing is, we've heard for decades that there really is no alternative to drop-in fuels. But if we look over a 30-year horizon, we can and we need to be much more ambitious than that. And we need to step away from things that we consider sacrosanct or are an idée fixe. Road transport has far more and much denser networks. Transforming is more challenging. Many more petrol stations than there are airports, really, believe me. But it already has several fuels. and aviation never really had only one fuel. You know, piston aircraft don't use the same fuel as jet aircraft. Obviously, Jet A is dominant. But, you know, frankly, if Henry Ford had considered drop-in fuel was the only alternative, the Model T would have taken a lot longer and would have burnt coal. It doesn't. And as they say, it's different strokes for different folks. We think new architectures will find their way into the market, and we think it's clear and it's absolutely fine that that will happen at the lower end of aviation. So shorter range, smaller aircraft, short commuter, general aviation, maybe even urban air mobility. There's going to be a role for pure electric. Some of that will be battery. Pure electric based on a hydrogen fuel cell. There's definitely a role for hybridization. We think there is a role that hydrogen can play beyond fuel cells in terms of a direct burn gas turbine environment. As others would say, you know, the rumors of the death of gas turbine are premature. They're going to be around for many, many decades. But the system is big enough to accommodate different solutions. And that is what we believe will be the case. This is the only formula I'm going to show, and I will make no attempt to resolve it. It's classical. It's the Breguet equation. Usually it's to say, or to determine what the range that you'll get out of a design given a certain payload. Conversely, you can use it for what payload you get for a certain range. But why am I showing it here? It shows the traditional levers that we have decades of experience in and have made phenomenal progress in. Aerodynamic efficiency, structural efficiency and weight, propulsion efficiency. And the one constant throughout has been the energy density, and it can no longer be. We can't afford to maintain that as something that is sacrosanct, because it influences everything. Of course, it's said often that if kerosene hadn't existed in nature, which it doesn't, by the way, it needs to be refined, but if it hadn't existed, then mankind would have invented it for aviation. It's pretty near perfect for as a liquid fuel for in the wings of an aircraft. But there are going to be other ways to solve the equation. Now, stepping across from where to start, how we start, and this is where I believe clean aviation can play a significant role, and I can get quite passionate about that, and I know my colleagues can, and our members can as well. As you well know, the European Union has declared very prominently a goal of climate neutrality by 2050. It will be enshrined in terms of its ambition and in law through the European Green Deal and the climate law. Along with the digital EU, they are the main drivers and the pillars, if you like, of the innovation cycle, of research and innovation, and therefore of Horizon Europe. Clean aviation is an instrument within Horizon Europe. So in the societal challenges, we'll find those all over the place. The Green Deal, climate neutrality, digitization. And a public-private partnership is a key instrument. Clean aviation will build, as Axel said, on earlier work in terms of partnerships, so Clean Sky 2, building on the results, taking lessons also in how things were done and how to improve. And also in the words of Sir Isaac Newton, we all know that when we're doing this kind of research, we're standing on the shoulders of giants. So a lot of work previously, whether Clean Sky 2, whether in the important and really significant work in national programs across the European Union area, or in earlier collaborative research work, many of the previous framework programs. All of this is relevant in terms of stepping stones towards where we want to go with clean aviation. Clean aviation has been set up as a public-private partnership, institutionalized, but I won't get into that detail in terms of how that's set up. I think that's a little bit beyond the scope of our introduction to you today. Its membership was formed with founding members, 27 in total, but has been expanded through a call for expression of interest in 2022, and now consists of 39 private members. Private, by the way, also means universities and RTOs, coupled with the European Commission on behalf of the Union. So that is the public partner. We work on the basis of open calls. Axel just mentioned it. We opened a call in March of this year. It closed on the 23rd of June. The evaluation kept a lot of people in our organization, but also in our membership, very busy over the summer. And luckily, we're now towards the tail end of this in terms of being able to take to our governing board for their approval the results of the evaluation so we can start the preparation of the projects and be operational. By regulation, no less than 30% reduction in greenhouse gas emissions shall be demonstrated prior to 2030, with an entry into service possible prior to 2035. And with the aim, and this is not trivial, with the aim of being able to have 75% of the world's fleet by 2050 incorporating these technologies. And this is beyond the fleet replacement of the, what I would call, neo generation. So this is replacing the neos. It's this clean sheet design, this technology level being the dominant factor in terms of the performance base for the fleet in 2050. And I'll return to that also later, because that goes well beyond what we can accomplish in terms of research and in terms of technology readiness levels. We need to factor in how we actually get this into the fleet in a way that allows everybody to earn their business and earn their keep. Now, that doesn't diminish the importance of the current fleet replacement. That's absolutely critical. As Airbus would tell you, Boeing will tell you, it doesn't in any way diminish the urgent need for scaling sustainable aviation fuels and to have them available in terms of an early low net carbon solution. The near-term challenges are also significant. The Green Deal speaks of 55% reduction in 2030 versus an earlier timeline. 2030 is tomorrow. 2050 is even quite close by for the cycles that we have in aviation, and that's one of our challenges. Yesterday, Brian Moran, a great friend of mine from Boeing, highlighted that each generation of aircraft has, on average, and I'm quoting him literally, a 15 to 25% efficiency gain. And that's true, and it's absolutely impressive. And no one, least of all we, are saying that that has been easy. And yet, we believe we need to double this. We believe the next generation, the 2035 generation of clean sheet designs, should skip a generation, should aim for 30 to 50%. We think that 30+%, for instance, on a typical single aisle mission is achievable, and our members tell us that that is achievable. It's not easy, but achievable. And our members tell us that up to 50% in a typical regional environment on a typical short-haul segment is feasible. Bruno Saint-Jean this morning also articulated that solutions will come from outside the traditional aeronautical sciences. We fully agree. And gratuitously quoting Eric Dalbier, who you'll see in a moment after this session, the CTO of Safran, and I love this quote from him. He always says, you know, we need to do two things. We need to use less fuel, and we need to use the right fuel. And if for no other reason, using less fuel, if that fuel is going to be significantly more expensive than the current fuel, is just as important as it is in terms of the emissions reduction. So we need both the economic benefit of using less of it and the emissions reduction. And by the way, you know, lest we forget, because sometimes numbers, they do kind of speak, we burn 1.25 billion liters of kerosene per day in the commercial aviation system. 1.25 billion. So if you're a young engineer, or perhaps still young, not like me, still undecided in terms of your career, not like me, I think aviation is one of the most exciting things that you can get into. And I hope really that we can attract the talent base that we're going to need. Because this decade is going to be the most transformative, if not ever, then certainly since the jet age. How are we structuring clean aviation? We have a strategic research and innovation agenda. This was adopted by the first board when the joint undertaking came into being through the regulation, linked to Horizon Europe, as I was saying. And the SRIA defines three thrusts. Go back and think about the distribution of flights over sector lengths. 1/3 up to 1,500 kilometers, 1/3 further up to 4,000 kilometers. So we're not saying that this is low-hanging fruit, but we are saying that we can make a huge dent in aviation's emissions by looking at that area of single-aisle, regional aircraft, short, medium range, regional connections. And this is not impact at TRL4 or demonstrating at TRL6. This is about how we get entry into service, how we get production rate run 100, how we can actually really make a difference by 2050. And the other thing is, looking beyond that in long haul, the state of the art at the big twin level of the A350 and the 787 is an area where, you know, a 30% performance gain is not something we're going to see tomorrow. And the airlines are not going to start replacing those aircraft. They're actually still in the well before the midway point in terms of the fleet introduction, being introduced to replace previous generations. So the day will come when the next long-haul aircraft can be 30% better. But that's not today. And today we're talking about the first thing we can do because we are in a hurry. Why is hydrogen in the middle? I get that question almost daily, but luckily there's been no lack of attention for the hydrogen agenda in these past 3 days. Are we so sure that hydrogen will be on board the next aircraft? The answer is we're not. If we were that sure, I think I would question whether we needed to fund it with the level that we are funding it between ourselves, the national programs, and the Clean Hydrogen Joint Undertaking, with whom we work extremely closely. I quote here John F. Kennedy. In his Man on the Moon statement at the time of the space race, he said, we don't do these things because they're easy. We do them because they're hard. And a liquid hydrogen-powered commercial airliner, if that entered into service, if we fly that before the end of this decade, that is an Apollo-scale challenge. Europe's Man on the Moon moment is pretty much if we have that in service, and that's a European product. And we should be darn proud of working on it. Very briefly, the program structure. Our strategic research agenda, defined by the members, took a look at this, came back very roughly with a two-phase approach. First phase up to roughly 2025, 26. Our first call, as Axel mentioned, is a big bang, a big bite out of the first phase. That aims to cover a pretty broad palette, but linked to the three thrusts. So only looking at regional, short, medium range, single aisle, and hydrogen solutions. But it's a broader palette in terms of what concepts, what options, what trade studies do we need in order to determine the down selection of things, because when we go from a study to a preliminary test, from a ground test to a flight test, the costs explode exponentially. So phase 2, from roughly 2025, will need a much narrower selection because we need to accelerate. We need to shift gears in phase 2 towards the end of the program. And again, because we're looking at an entry into service prior to 2035. Now, we can't go it alone. The program is 4.1 billion. That is, by the way, 1.7 billion in EU funding, 2.4 in private. So the leverage factor in doing this is very healthy. But we're going to need to work on synergies. And I'll come to that in a moment. But this ATO, authority to offer, as it's often called, within this decade, because otherwise you won't have an aircraft entering into service in 2035, is actually stated as ambition in the regulation and is a key feature of this program, impact-focused program. So we very much see clean aviation as a central hub in a kind of a hub-and-spoke network. Again, referring to Bruno Saint-Jean, different disciplines can bring really important contributions towards a different architecture of aircraft with this big change in emissions profile. We can do this together with the national programs. There are contributions that can come from regional innovation programs, and evidently at the European level, collaborative research, clean hydrogen, which again we not only are next door neighbors to, but speak with on a daily basis and work with very closely. CESAR joint undertaking, equally. But also batteries, key digital technologies, the fuel, the SAF initiatives, they are equally important for us. And just coming to the end, I'd like to highlight one other point that for us was a very strong encouragement. We decided and we had a need to do a socioeconomic analysis, which we contracted for and had a study performed. And in effect, when doing so, we asked the contractor, so the group doing this study, to take a look at the post-COVID, the likely scenarios. So not one deterministic approach, but the likely scenarios. And you can imagine here, and you've probably heard of this before, how will the aviation system recover? I think what we're seeing, and aviation is again almost a victim of its success, we're seeing aviation recover because the queues in front of security are, in some cases, quite annoying. The airlines are struggling to have the manpower to fly versus the demand that's being recovered. So there is a recovery. But it might well be structurally asymmetric, different ways of flying, different routes, more leisure than business, etc. There might be more or increased regulatory scrutiny, consumer behavior. It's not a given that it stays the same. We did a stress test, and the result was resoundingly positive. The SRIA came out looking as fit for purpose, meaning every scenario it touches, and it touches in a credible way in terms of making the biggest difference. The focus on short, medium range, regional, and hydrogen. It's essential. But in closing, what I'd say, it's essential, but it's not enough. Because we're not talking about one demonstration. We're not talking about the lab. We're not talking about taking the lab to a demonstrator. We want this to be in service. And as the saying goes, if you want to go fast, you go alone. If you want to go far, you go together. The problem is we need to go far, fast. and that's a challenge. And only a system of systems approach will help us here. Think of Thomas Edison. There would have been no point in a light bulb if there was no plan to put an electric grid in place. There's no point in flying a hydrogen aircraft once if there is no plan for infrastructure in place at the same time. We need synchronization across a system of system approach. We'll need a faster, so outside the essential research, we need a much faster time to market approach, and that will impact certification. So it's good to see that certification is actually one of the core areas that we're trying to address transversely across clean aviation. We're going to need faster fleet replacement. And that's not just production, but making money making these aircraft is important. Airlines need to be able to make money after having invested in these new aircraft at a rate which is much faster than before. We need the scale-up of SAF. We need to continue to work on single European sky and ATM. We need airlines to continue to look sensibly at what air networks will look like. And finally, it's been said a number of times over the past 2 days, and I would really like to reiterate that, non-CO2. We have to complete the journey in terms of getting a full understanding, but not just an understanding. We also need much more effort into understanding and actioning the mitigation scenarios, the mitigation approaches to non-CO2 effects, whether that's water, water vapor, contrail formation, cirrus, or NOx. Sir Winston Churchill once said, but in a very different context, and in closing, after clean aviation, we're not at the end. We're not even at the beginning of the end. We may be at the end of the beginning. So this journey is just taking off. Thank you very much.
Thanks a lot, Ron, for setting the scene a little bit and highlighting the key drivers, the key ingredients of the program. Maybe you stay for a second and we'll see whether there are some questions or comments from the audience. There's one up there. Yes, please.
Hello, my name is Pauline. I work for Ampere. So you talk about short and medium range flights and within for existing routes to replace those aircraft, make them more efficient. But do you think we should also look outside of the aviation sector? I know that the aviation sector is currently responsible for 3% of the emissions, but then the transport sector, I think somebody said, was 17% responsible for emissions. So offering even shorter flights, maybe we could even cut more emissions, but outside of the current aviation sector. But do you think this is a possibility, and do we need to maybe reconsider the way aviation works right now? So instead of having a hub-to-spoke model, go to demand point-to-point flights? Is that something you look at all, or just the existing short ranges?
That's I think 3 points wrapped into one, but I think you raise very relevant ones and very intriguing ones. To start with the latter one, that's what I referred to also in terms of the so-called stress tests. I think the jury is out in what the aviation system will look like in 2050. I think it would be naive to assume that the current networks will remain unchanged over that duration of time. And the nature of technology disruption is it actually enables people to look differently, and perhaps there will be new players at the air operator level rather than the current ones that take new ideas into a different format, a different way of flying. And you mentioned point-to-point versus hub and spoke. And one could well imagine that happening and alleviating the let's say congestion at hubs and flying differently. What can happen, because we've looked at that a little bit, is you try and factor in disruptive technology. You can fly fully electric, say on a battery, with 10, 15 passengers over the next 10 years. If you aim to replace an A320, then you're going to need 10 flights replacing one, and that's going to have some serious impact in terms of the, let's say, air navigation, so air traffic management. So I think the jury is out in terms of how quickly those kind of new models will infiltrate the overall system. Finally, you mentioned aviation replacing other modes of transport. I think, clearly there are initiatives, very many initiatives that are looking at urban air mobility. You can bypass congestion on the ground, but if you're flying electrically and thinking that's zero emission compared to road transport, you can also develop electric road transport. And staying on ground is more energy efficient than flying, generally speaking. So I'm personally speaking, I'm a little bit skeptical in terms of energy reduction overall by flying as opposed to ground transport where you can. But it's a very vibrant sector with a lot of new ideas, and I think it's exciting to see how that pans out.
Thank you. If there is no other urgent comment question, then I would like to thank you to Ron, and over to the second presentation this afternoon. Second presentation is about the thrust, one of the thrusts, the short-medium range thrust, so ultra-efficient architectures at aircraft level, but also at propulsion level. And we are going to listen to Maria Calvo Blanco, and Maria has a degree in aerospace engineering. She started at Airbus as a loads engineer in Madrid in Spain on the Eurofighter, on the C295 and on the A400M. Then she moved to the UK, became flight control, working in the flight control loads area for A380 finally, and then returned back to Spain and became domain leader of static loads and power plant interface at Airbus Defence and Space. Finally, she joined our organization, the Clean Aviation organization, just in May this year as a team leader for the short medium range aircraft technologies. Maria, please.
Thank you, Axel. And thank you to ICAS to give us the opportunity to give the vision for the ultra-efficient aircraft and propulsion architectures, our vision within clean aviation. So I'm delighted to join Clean Aviation because actually it's joining two of my passions, aircraft design and sustainability. And in my career, I always followed a quote that I would like to share with you, is that do what you love and love what you do. And what I do love from Clean Aviation is that we are part of a bigger picture. We are part of the European Green Deals, and we are focusing towards climate neutral aviation. And this is really an integrated architecture where there are many players, starting from researchers, starting from universities, but also manufacturers, operators, public sector, and the end users. And there will be also a lot of investment to get the new energies ready and infrastructures. But what is our contribution? What is our ambition in clean aviation? Our ambition, and is part of the thrust that I will present to you, is to ensure that there are breakthrough technologies that are ready and will allow new developments by 2030. So we will have aircraft entering into service in 2035. So these are the clean aviation three thrusts that Ron presented before. So we will have these three sessions to give you a hint about what is the vision and what we are envisaging in terms of technologies for them, for hybrid electric regional aircraft, for the short medium range, and also the disruptive technologies to enable the hydrogen power aircraft. This started with the strategic research innovation agenda that Ron also mentioned, starting back in 2020, and actually creating a roadmap in order to achieve these goals of really having a product that is capable to be entering into service 2035 and be able also to replace the fleet by 75%. And the fundamentals of this roadmap are a thing that I think most people in this room will agree on. The fundamental is that an aircraft is a very complex system and is safety critical. So if you want to introduce disruptive or innovative technologies so that they are ready for entry into service, so to certification, you have to evolve in an integrated way and have an acceleration for technologies with demonstration and with an integrated view. So that's why we have these two phases. The first phase, we just started with the call this year, our first call launch, and will be dedicated to develop the concepts, the technologies, the different options and trade-offs that we need to do before going into the acceleration phase 2 to maturate through an integrated demonstration. And now focusing more on the short, medium range targets. So how we are implementing these objectives. First, which are the targets, and then how we are implementing. The targets are aligned to what has been presented before in other forums. So we are targeting to improve no less than 30% of the energy efficiency on a typical mission, compared to the 2020 state of the art. For what is a typical mission that we are targeting? So the typical mission is a segment capacity from 100 to 250 seats and up to 3,700 range. Ron presented some pictures why we are focusing on that area, but just to give you a takeaway, is this contribute to 2/3 of the global emission for flights. So it's really an important area where we need to focus in order to bring impact, because clean aviation is an impact program. And to do so, contrary to what we could do for smaller range, smaller missions, that you could use hybrid electric solutions. And actually, maybe I can recall the ones that have seen the IFAR presentation this morning, the first one. There was a nice chart about the electrical battery limits. So really, what the batteries can bring us and electric solution as a single core energy source for short, medium range are not ready, are not enough. So that's why the target for our short, medium range solution is to based on ultra-efficient concepts, ultra-efficient aircraft and ultra-efficient propulsion systems. The less fuel that consume, the better. So this will be essential for the transition to low emission consumption to zero emissions in the future. The target is 30% fuel energy reduction, and a big part of it will be part of what can be brought from the propulsion system, because we are targeting that at least 20% is coming from fuel reduction. The roadmap does not include only drop-in fuels, but we are also having some of the area dedicated to the demonstration for more disruptive concepts using hydrogen. And this is linked to the third clean aviation thrust that will be presented today, where we are aiming to develop technologies that are enablers for a hydrogen-powered aircraft, targeting at least 15% reduction. And to achieve all that, it's very important to have an integrated approach with an innovation architecture, making strong links between the technology development and the product development and certification. So we think that our program could be a really this forum where we can strengthen these links between academia, research organization, SMEs, and large industrial enterprises. Which are the challenges that we have in front of us to reach this ambition? So, first of all, overall aircraft concept, also greener industrial backbone, so less waste, reduce manufacturing timeline, and novel certification methods, together with the classical ultra-efficient empennage design, airframe, fuselage and integrated systems design, ultra-efficient wing, and last but not least, the efficient integrated propulsion systems. So if you have seen the call one that we have launched, maybe after what I explained, it's clear to you that we have three main topics focused on short and medium range, up to 207 millions, and then two transversal areas that will be focused on developing the aircraft concept and also the novel certification methods that are needed. I will go a little more in detail about the type of technologies that we are aiming for each of these topics. So for SMR01, which is the ultra-efficient propulsion systems, the proposed solutions and technologies are expected to start at TRL 3 and be able to achieve TRL 5 at system level. So they are ready for ducted or unducted engine architecture. Christophe was presenting before for Clean Sky 2, what are the type of architectures that has been explored. There are also core engine and combustion technologies investigation that are expected to reach TRL 4. There are three main areas for the benefit, which are clustered in smarter engines, lighter engines, and cleaner emissions. Smarter engines, there is some examples here, like variable geometry, so pitch multi-blade devices, or finding the optimum conditions for different flight modes, electrical machines for the transmission systems, innovative thermodynamic cycles, or changing the way of controlling the engine, for example, with artificial and intelligent. Lighter engines, reducing number of components, changing materials, new architectures, but also multifunctional systems that will reduce weight. And cleaner emissions, so not only CO2, but other type of particles that can be reduced, managing byproducts, creating new way of dealing with the water extraction system, reducing contrails, changing the way of the combustion, so you got always an optimal combustion, so you reduce your emissions. So these are the three areas that we will focus in the propulsion systems. For the ultra-efficient airframe, and I put here together the wing, fuselage, and empennage, even if they are two different topics in our call. So again, some examples here, how we will reach a maturation for TRL 4 or higher in order to get ground test and also possible scaled flight test demonstration for these technologies. So we aim to achieve new materials. The multifunctional fuselage was presented today. This could be like a taste for you about what could be. Integrated structural elements, so the systems are even more complex in the new aircraft concept, so we need to get a more integrated airframe in the end. Modularized concept, something that is more standardized, more changeable, and we can evolve for the future to new configurations. And then also optimization of load distribution in order to reduce the weight and the drag. Sustainable industrial system. You remember I mentioned one of the objectives is also to have a footprint in the green industry and what is the effect of the new technology that we're introducing in the life cycle of the technology. And last but not least, of course, the low drag and high aspect ratio solution that has been also mentioned before from one of the Clean Sky 2 outcomes. And then we have the transversal topics. Really important, driving, what will be done, what will be developed in the technologies for the wing, for the fuselage, for the propulsion system. And here, what I wanted to put here is phase 1, not phase 2. I'm so excited to go to phase 2 that I put here the phase 2, but actually we are in the phase 1 that will be selecting from all the technologies that are promising and that we can evaluate that they have an impact on the greenhouse emission, on the life cycle optimum solutions. We have to down select with the view of that this has to be integrated in a full aircraft concept, able to be certified. And that's why we need to explore also new means of compliance, maybe challenge the requirements that we have. If we are asking a high aspect ratio, you have maybe, I think Jerome explained before as well, you are near of the flutter area, you have to introduce flutter control. This impacts certification. And we have to take it into early design, all these concepts. But we are not doing that from scratch. And we are building up on Clean Sky and Clean Sky 2. And probably now you see the link of, if you have attended the session this morning, there are a lot of links to what has been presented this morning. First is that we are relying on the network that has been created, the consortiums, the partners, the beneficiaries, from universities, research centers, small and medium enterprises, and OMEs. And these skills and competencies are bringing some of the results that we need to make the short and medium range ultra-efficient aircraft a success. We have the open fan solutions, the high bypass ratio engine, ultra-efficient engines, laminarity solution that has been tested, hybrid laminar solution for tail and for the wing, small-scale demonstration, and integration of different concepts, new materials, new way of integrating the systems within the aircraft. And it's not working, the next one? Okay. And the takeaways, well, I agree with my colleagues that this is the most exciting technological decade for aeronautics, and I'm happy that I joined Clean Aviation in this period. So we have to keep pushing the envelope in the traditional technologies, so the low drag solutions, weight reduction, optimized methods, and concurrent design. And it will be, in this program, a step further for us to move from really technology development to integrate all these in an aircraft concept that will be a product development. But then we have also to build up in non-traditional disciplines. New materials, disruptive methods and concepts, digital solutions to get everyone connected and to share more efficiently data and methods, and to enable certified solutions. So we need to establish also an early exchange with the certification authorities. And last but not least is the end-to-end aspects that we need to include that in early design in order to be able to establish what is the life cycle footprint of the technologies that we are offering. One, that you enter a new technology, you need to evaluate if this is adverse for the different system in the aircraft integration and for the overall aircraft view. And the maintenance and in-service impact. If we are proposing the adequate no-waste culture and recyclability for it. So this is our ambition. And I wish that most of the people in the room will follow us and engage with our projects and be part of the new generation of aircraft. Thank you.
Thank you, Maria, for excuse me, giving us an insight into the SMR thrust. Are there any questions? Are there comments? Do you think that's realistic? Do you want to be part of it? Yes, please.
Good afternoon, Medical Raminasa Langley. On one of your charts, you had a statement said novel certification methods. Could you please expand what is meant by that statement? I mean, are you talking about sub-components certification by, let's say, manufacturing groups, or is that aircraft certification?
Yes. Yeah, thank you for the question. Yes, I did not elaborate much on that, so I will do now. So actually, it's at aircraft certification level. So it's we have first to review if the means of compliance that we have today. We are starting with more in the CS25, more close to our European perimeter, but it will be applicable to FAA rules. So the ambition is to be able to present something that will be workable also outside Europe, because we have a worldwide flying fleet. So it's aircraft certification, and we will be evaluating if the means of compliance, current means of compliance are enough, the requirements that we have are adequate. One example, I think I briefly mentioned, is if you include active flutter control for a very high aspect ratio wing, you really have to renegotiate and re-evaluate which are the means of compliance and requirements that you have to meet. So it's at aircraft, mainly at aircraft level, in order to have a product that is certifiable, and we assure that we have the entry into service in 2035.
So just to add on that and to build on that, I think it's very important, and that's also for us a kind of first-time approach that we are including EASA, the European Certification Authority, at this very onset of a program into the research task. So EASA is going to be part of various research aspects there in order to grow the research together with the consideration of all the certification aspects, and that we are not being in 2030, if we are projecting ourselves into 2030, and then starting with some certification requirements. I think those requirements need to be embedded into the research work right now, right from the onset of the program. And I think that's something which we have not been doing in the Clean Sky 2 context, but we are going to focus on now in Clean Aviation.
So is that the novel part, that you're going to embed the certification early on into your process? Is that the novel part? Because I was interested in what is meant by that novel certification.
We are aiming also to get more involved with EASA, so they get more connected, we'll say, with the industry, in order also to shorten the certification period. So now certification is really based on papers, tons of papers, and reading nice, good papers that the EASA and other certification authorities need to read, but it's really heavy workload that if we introduce also the digital framework, taking into account that we have now more benefits with the IT connection, and we are able to agree a way of connecting more efficiently with EASA and to prove more efficiently that we have met the requirements that they are asking us to prove the safety of the aircraft, that will reduce dramatically the certification time, and will be key to get new innovation technologies on board, because if we have a technology demonstration by 2030 and entry into service, 5 years for certification is also quite challenging.
The point here is also that in certain areas, when you think about hydrogen, we are going to come to that in a minute, there is not a lot of certification basis. So that's why there are many white sheet of papers, and I think that's why it's so important to embed EASA very early into that process in order to grow that competence, that knowledge, at the same time on the technological side, but also on the certification side. Other comments, questions? Yes, please.
Yes, Mark Page here from Jet Zero. I was curious about the composites work that you were undertaking. Could you describe a little bit more the breadth of alternative future carbon and whatever material concepts you're pursuing? Are you going beyond Vardum, beyond thermoplastic, or is that the emphasis sort of in that area?
Thank you for your question. Actually, I cannot give you that insight by now because that will be the outcome of our phase one, which are the most promising technologies and which type of materials which help us to achieve these goals. So exactly that it will be what the different consortiums that now we have been evaluating this summer will be working in the next months and year, and in order to select which are the technologies that are more promising and align with the target of the greenhouse gas emission reduction.
We heard this morning, but probably you haven't had a chance to listen there to one of the speeches, the multifunctional fuselage demonstrator based on thermoplastics and welding. I think that's definitely a concept we are going to pursue. Whether that's the final one to be selected, who knows? But that's definitely one which is part of the selection process. Other comments, questions? Yes, please.
Hi, yes. Thank you very much for the presentation. It was definitely very interesting. And I would like to ask, in terms of your perspective for women in engineering, whether, I'm not sure if clean aviation is obviously focused on the sustainable side, but what do you feel can be done or is being done for taking up more women in engineering, because obviously in many companies there's a low number of that.
Well, thank you for your question. Yes, I have always been quite alone in some meetings, not being the only woman in the room. I remember maybe one meeting in Clean Sky, actually, in the Smart Fixed Wing aircraft. There were like 50 senior people in the room, and I was the only young woman. So, but I think things have changed a lot since that. That was almost 20 years ago. And I have observed a lot of effort from the industry, and also I think in clean aviation we are quite a multicultural team and diverse team. So I have seen that there is a lot of impulse in the industry to get more involvement of women in the different areas. I have always feel really privileged to work with my colleagues, and I have not feel put aside because of being a woman. On the contrary, I have been really given a very nice opportunity. So I think we have evolved a lot, but still we have some things to do. And actually, what we need to do more focused in my perspective, and I'm contributing to that, is to mentor young women that really like science and engineering, and doing mentoring. There are very nice programs where you can collaborate as well, either if you are a woman or a man, to really encourage young talent, young women to join us, because in the end there's a percentage that is low, so we need really to do this mentoring and this encouraging of young talent.
Thank you. Are there other points, other questions? Any comment? No, not the case. Then thank you very much, Maria. And we are moving over to the next presentation. Hybrid electric or full electric, focused on the regional aircraft segment, as you have seen already, the focus area, so the second thrust, as we call it, and we have Antonello Marino providing us with that presentation this afternoon. Antonello has a master's in aerospace engineering and a PhD in fluid dynamics. He worked a long time in Alenia, previous Alenia, today Leonardo, as a structural and aircraft loads engineer. Later he became program manager in different aircraft programs, and since 2016 he joined Clean Sky, and he has been a project officer, and since this year he has been nominated just recently as team leader hybrid electric. Antonello.
Thank you, Axel, for the nice introduction. Good afternoon to everybody. I'm very pleased to be here this afternoon and say a few words around the hybrid electric regional stream in clean aviation, in particular concerning the development of hybrid electric and full electric architecture for low emission hybrid electric regional aircraft. In this respect, I would like to highlight the context in which the activities are performed by recalling some of the information just said before by my colleague Ron. Actually, 2/3 of the overall global emission are from fly ranging below than 4,000 kilometers, and actually 1/3 are from fly ranging for less than 1,500 kilometers. So in terms of market share, the regional aircraft covered overall the 12% of available seat per kilometer. And in terms of connectivity, 40% of existing airports mainly rely on the operation of turboprop regional aircraft. So although the regional aircraft sector in terms of global emission only contribute, in aviation, only contribute to the 5% of emission, in terms of market share clearly play an important role. And we do expect that if we succeed in the plan, in the program that I'm going to show later on, this market share may even further expand. And as I said, in this context, the ambition of clean aviation into the hybrid electric regional stream is to develop technologies and innovations that when integrated into a regional aircraft, 50-100 packs, enable fuel burn reduction of a minimum 50% compared to reference aircraft. And according to the planning, in the first phase of the program until 26, we will mainly mature again the major technobricks. The final demonstration in the second phase by the end of the program is an hybrid electric regional aircraft, actually integrating the most promising technologies which have the potential to enter into service by 2035. As said by my colleague, in this respect and to achieve the desired goal is really we need to continue pushing all the traditional discipline in aeronautic, but of course for the hybrid electric regional segment, we clearly need to open the mind to new ones. We need also to continue investing and developing our manufacturing capabilities. From one side, toward the development of a lighter structure that will be important for this kind of aircraft, but from the other side also to secure our manufacturing capability to finally afford the fleet replacement that it is expected to take place from 2035 onwards. In this respect, the life cycle aspect and recyclability are considered important as well. And again, we need to work also in parallel with the new simulation and the new innovative certification methods. I don't want now to open the discussion previously said, but clearly for the integration of hybrid electric powertrain, we need to trigger new discussion with the different certification authority to define the means of compliance and to finally reach a certifiable aircraft. Concerning the hybrid electric regional stream, how we are going to achieve the desired goal. We have clearly identified the area of development, the area of intervention, the enabling technologies. These are the hybrid electric powertrain, the electrical distribution system, the airframe integrated wing and integrated fuselage, and the thermal management system. As mentioned by Ron before, we have recently launched the first call covering 700 million euro for 14 topics. And focusing on hybrid electric regional stream, we can identify 5 topics with an overall budget of more or less 200 million euro, covering almost all the mentioned areas. We will enter in each of the topic in a moment. Focusing now on the powertrain, I guess we all recognize the big improvement which has been made in the last year in terms of efficiency in electrical propulsion. However, and related technologies, so fuel cell, batteries, electrical motors. However, we must recognize that not all the technologies that have been developed for small aircraft, as example, can be simply scaled up to larger aircraft. Meaning technology that are now available and have been integrated in 2-4 packs passenger aircraft are not going to scale up to large regional aircraft, 50, 100 passenger, 1,000 kilometer range. An evident limit is the energy storage. The specific energy of a battery is today around 150, is between 150 to 150 watt-hour per kilogram, which a big improvement is expected in the coming year, but still will remain far away from the specific energy of fossil fuel, which is more than 10,000 watt-hour per kilogram. So that said, we recognize that the full electric aircraft in the regional domain is on the table, but far more likely to be fuel cell-based rather than battery-based. In this context, hybridization is seen as a good opportunity, is an option, where the power from the fuel burn is reduced via electrical boost power provided by the electrical motor. So in this context, we will see a different solution emerging using batteries, fuel cell, a combination of two, but we also see thermal engines still operating for some years. And years in aeronautical sector is decades, not is decades. So we need also to continue investing in improving the efficiency of this unit as well. Well, all this aspect will be covered under the HR01 topic, the multi-megawatt hybrid electric propulsion system, where we target to deliver hybrid electric multi-megawatt propulsion system able to deliver a total shaft power between 4 and 10 megawatt. Of course, the propulsion system may be composed by a multi-powertrain module with a minimum power of 1 megawatt. And here the ambition is to develop an architecture that is able to deliver no less than 30% of gas emission reduction compared to reference propulsion. There are no single option. There are no single path, so different configuration need to be assessed. Different configuration of hybrid propulsion, parallel, serial, combination of two, different level of hybridization, and the final target for the first phase is to reach at least TRL4 at the powertrain level, or higher, but also with a clear roadmap toward the TRL6 by the end of the program. Moving to the electrical distribution system, I guess here is interesting to recall the trend of electrical power capacity of aircraft over the last years. Boeing 737 started its operation with a power capacity of about 80 kilowatt ampere, so around 100 kilowatt ampere, and in the next years, no big increase of power capacity in aircraft was seen. In fact, the power capacity only reached 200 kilowatt ampere in 2000, and only in the last years we saw a big increase of power capacity and demand into the aircraft. From one side to accommodate the entry into service of more electrical systems, and the other side, of course, also to support the entry into service of a larger aircraft. However, when hybrid electric multi-megawatt aircraft are concerned, the first issue that comes to the mind is the integration and the usage of high voltages and high current in a constrained environment. So power modules need to be to operate in under unpressurized conditions, low air density, and many aspects, many challenges need to be considered, such as arcing, magnetic interference, insulation issues, partial discharges of electrical component. Well, all these aspects will be tackled under the topic HR03. Again, the scope is to develop a reliable and safe electrical distribution system for our hybrid electric multi-megawatt aircraft, high voltage network, more than 800 volt, but also keeping an eye on the weight penalties, which should be no less than 20%. Again, the ambition is to reach TRL5 in this case at a system level by the end of the first phase, again with a clear path toward TRL6 by the end of the program in the second phase. Moving now to the thermal management system. Conventional propulsion system mainly disposes all the thermal loads through the exhaust gases, while the remaining thermal sources are driven away from the conventional heat sinks, oil, fuel, air. However, when hybrid electric system need to be integrated into the aircraft, one of the major challenges is the waste heat from the electrical component. Just an example, the fuel cell efficiency is in the range between 40–60%. This means that 1 megawatt of fuel cell integrated into the aircraft will finally result in more than 600 kilowatt of thermal energy that need to be dissipated. Overall, for an hybrid electric regional aircraft, we estimated about 1 megawatt of thermal loads need to be dissipated, compared to the today 100 kilowatt. In terms of comparison, we are moving from an house to a village. All these aspects will be tackled in the HR02, where the ambition is to develop a thermal management system for a hybrid electric regional aircraft with an improved efficiency and again with a weight penalty less than 30%. Also, the target here is to reach TRL5 by the end of the program, and a clear path toward TRL6, TRL5 by the end of the first phase, and TRL6 at the end of the program. We are moving now to the airframe. For what concerns the previously mentioned enabling technologies, we must recognize that they are enabling technologies, so we need integration of this technology to achieve the desired goals at aircraft level. However, they will also bring extra weight. New component, bigger component, heavier component need to find space into the overall aircraft architecture and airframe. And this extra weight need to be compensated in a way or another. Clean Sky 1, Clean Sky 2, but also other national and European projects has demonstrated that weight saving can be achieved by working on an introduction of new materials into the airframe or new manufacturing process and assembly processes. Well, many activities were performed in Clean Sky 2. This morning, Sebastian and the other colleagues have clearly showed some of these activities. We believe that results from this project, less or net, will support, will contribute to the clean aviation in this aspect. We have not, as you have seen before, we have not launched a specific call covering the fuselage the integrated fuselage in hybrid electric regional aircraft. Clean Sky 2 is now in the delivery phase of the program, where major results will be delivered. The viability of certain solution will be confirmed. So we believe that it was worth to wait for this result before launching a specific topic on that. But of course, clearly, this is one of the aspects that need to be addressed in the next future. The same consideration can be made for the wing. Again, many activities were performed in the past concerning a more efficient wing from aerodynamic and structural point of view. Again, we do hope that this result and lesson learned will support the development of a more integrated wing for the hybrid electric regional aircraft. In particular, will support the activities that are planned under the HR04 topic, innovative wing design for hybrid electric regional aircraft. Again, here, the final mission is to deliver an innovative, high-efficient wing with more than 20% of structural weight reduction at fuel level. And in terms of performance, the system, when integrated into aircraft, should contribute to more than 50% fuel burn reduction. Again, to achieve this goal, clearly, optimal solution from a aerodynamic point of view need to be combined with structural one. And the final ambition, again, is to reach Tier 5 at the end of the first phase, with, again, the ambition of reaching Tier 6 at the end of the program. We are now moving to the over-aircraft design, which is one, and performance assessment, which is one of the aspects, which is the aspect that is addressed under the Tier 01. Here, the ambition, as I said, is to develop and deliver up to a typical design review, high potential disruptive hybrid electric regional aircraft, which integrate all the mentioned enabling technologies. Clearly, we may envisage the need to open the design space to new architecture of aircraft. From one side, to meet the requirement coming from the integration of the different subsystem and enabling technologies, but from the other side, also to support, also to identify new optimal point in terms of operation, in terms of mission, in terms of flight physics and aircraft performances. Here, the overall ambition is to reach 50% of fuel burn reduction, is to develop a configuration, actually, which is able to deliver more than 50% fuel burn reduction for a typical regional mission compared to 2020 state-of-art reference aircraft. Well, I'm at the end of my presentation. I want to say that basically, I hope that with the best of my capabilities within the given time frame, I was able to show you the main future of the hybrid electric regional stream in clean aviation, but also some of the main challenges. However, I want also to share but also our optimism. We are not starting from scratch. Many capabilities have been developed over the last year in Europe, in previous programs, and now are available to support the implementation of this program. Capabilities, meaning capabilities in developing novel aircraft architecture, more efficient propulsion system, advanced airframe. Let's not forget our testing capability on ground and on fly to validate and to mature our technologies in relevant in real environment. And finally, let's not forget all the skill and competencies that have been developed and now available in Europe and across the world. Well, our ambition is to collect all of them and make them working together toward a successful but also impactful program. Thank you.
Thank you, Antonello. And again, the question to the audience, are there any comments? Are there anything else you would like to know about the hybrid electric thrust? There is a question in the middle there, please. Oh, no, then we start there, please. Okay. Yes.
Good afternoon. This is Gaudi from NASA. Yes, excellent program that you've laid out. And a couple of questions. First is, I understand phase 1 is TRL maturation to 5, and you're planning for a TRL 6 maturation at the system level. At the end of the program, is that 2027 timeframe?
Let's say by the end of, by 2030.
By 2030. No. I did note that you have a scaled test bed. Is there plans to test the hybrid electric architecture at the regional level in a test bed, flight test bed?
Yeah, this is the idea. The final ambition is indeed to develop a flight demonstrator integrating all the different enabling technologies for an hybrid electric regional aircraft, and the flight test this demonstrator in order to validate the different technobricks. Again, when we talk about integration of technology, we are talking about technology that are also potentially can enter into the market by 2035. So should be also very mature and to achieve this goal, and no barriers should be detected as example from a certification point of view.
And this flight test demonstration would happen in the 2030 timeframe also?
Yeah, by that time. This is our ambition.
Okay.
And our target, I hope.
It's very challenging. Really appreciate the work that you're doing.
We don't know.
Yeah, we have two phases, as Antonello said. So the first phase, 25, 26, and then the second phase, which is consisting of the bigger flight demos and the down selection of the technologies to be brought onto the flight demos. But those are not decided yet, because that depends very much on the results of the technology development work in the first phase. Yes, please.
About the certification plans that you have, or maybe your opinion into how you're planning to certify these different components from the powertrain, as a hybrid will have different systems, right? So you'll have, in the case of a series, for example, would you think of certifying the power generation part separately or the electric motor separately?
Yeah.
Your ideas on that?
Well, honestly, I don't have the answer for that, but we know that this is one of the challenges inside the program, because when we integrate new technologies in aircraft, clearly we need to tackle this issue. We, as I've mentioned before by Axel, actually we don't know that in the overall Clean Aviation program, the ambition is so high that certain aspects need to be anticipated. This is why EASA is a part of the board of Clean Aviation from the beginning. It is expected that EASA certification authority will work and will support the development of each technobrick, and together with the major EM, they will define the certification path, the certification plan that finally will allow the different technology to enter into service in 2035. So nothing is defined, but the path to achieve this goal is done.
Thank you very much.
Any other comment, question? Don't see any hand anymore.
Hello, Frederick from Saab. I was happy to see that you took up the cooling requirements. Could you elaborate a bit on that and how much energy would be spent on cooling?
Well, as I said, according to our estimation, which was made also with the support of the major EM, with the cooling system for the next generation of hybrid electric aircraft should be able to dissipate up to 1 megawatt of thermal energy. Yeah, I know it's a big challenge. It's one of the big challenges that is in front of us. So really new cooling system need to be developed and the solution. An example, I don't want now to talk a lot about that. Clearly, as example, the usage of liquid hydrogen in fuel tank may open a new cooling solution that need to be considered in the development of a more integrated thermal management system of an hybrid electric regional aircraft. But the overall power that needs to be dissipated, according to our estimation, is up to 1 megawatt.
Thank you.
Welcome.
So, another chance? No more? Maybe a point from my side, Antonello, with regard to the bricks to come from Clean Sky 1, 2, maybe also from other programs, from national programs. How do you consider that? With how much upfront benefit do we start already? Is that, let's say, half of the work which needs to be done? How would you see that? How do you see the work which has been performed already? You were partially part of it already. Other work happened in parallel streams. How important is that for the success of clean aviation?
Nice and quite difficult question, but, Axel. But indeed, you are right. Many activities, many results are available and were performed in previous program, Clean Sky, Clean Aviation, and so on. Focusing on Clean Sky 2 as example, we know that the two programs worked really covered all the subsystem of the aircraft, and many solutions have developed for each single subsystem of the aircraft. We hope that some of the solutions that have been matured today, up to TL 4, TL 5, are suitable for further development and may contribute to development of hybrid electric regional aircraft. The problem is that for sure there is a gaps between the today technologies and the target we have. We are integrating and completing new architecture. Well, this gap can only be covered with implementation of new activities and by discovering day by day the different challenges. If I may, maybe among the different activities that I would like to mention in Clean Sky 2, for the hybrid electric regional aircraft, clearly we are going to develop a completely new architecture of aircraft. Maybe the shape will be more or less the same, but at aircraft level, we are talking about the integration of a completely different architecture. And in this context, I believe that the capabilities that we've been developed in Clean Sky 2 under the novel aircraft concept, the stream that we have in Clean Sky 2 are very important. And I hope that these capabilities that are not so common at aircraft level will help us in the development phase of the program.
Mm-hmm. Yeah, thank you. Yeah, I think that's probably one of the I may call it challenge or opportunity, depending a bit on how you see it. All those technology bricks which have been developed in the Clean Sky 1, Clean Sky 2, the collaborative research at European level, the national level programs. There are programs in various European countries supported by regions, by states, to make sure that all of those technologies, all of those content is being integrated and pre-selected, down-selected, the most promising ones, and then being brought into phase 2 at the right point in time, so that we can concentrate in phase 2 on the most relevant in order to get to a solid TRL6 with regard to the performance targets we have been indicating today. So that will be the challenge, to mature the technologies in the pipeline in phase 1, but also to prepare the conceptual work and the demonstration work then to be launched for phase 2. I don't see any other question or comment, so then I would suggest we go to the last presentation of this session, which is, thanks a lot, Antonello. The last brick, the last thrust in that exercise this afternoon is going to be hydrogen. So probably, yeah, if not the most challenging in this context, not just from a technological point of view, but also from an infrastructure point of view, from an operational point of view, in terms of airline operations. And we have today Paolo Trinchieri providing us an overview of this thrust in the Clean Aviation Partnership. So a few words related to Paolo's background. Paolo has a Master in Aeronautical Engineering from Torino. He started his career in Fiat Aviosystem engineering department beginning of the 90s. Then he was project manager or program manager for various civil and defense programs between 97 and 2005. In 2005 to 2013, he was the R&T program manager in Avio Aero, and afterwards he joined the Clean Sky 2 program. At that time, yes, it was already Clean Sky 2. And then nowadays, he just took over the team leadership for the hydrogen thrust. So that's going to be now. Please, Paolo. Please.
Thank you very much, Axel. Thank you very much. Good afternoon to everybody. Yes, I see that we are perfectly on time. So yeah, I try to be efficient as the colleagues did. So I'm a propulsion engineer, and yes, for hydrogen, the engine is only part of the game. We have also other systems that are as well interesting to be developed as part of the challenge. So we're talking about disruptive technologies here because, first of all, this is a new field in clean aviation, but is also, I may say, a new field also for the aeronautical industry, to try to scale up and build a path for a possible future welcomed hydrogen aircraft for short-range application. So I would start from this chart. This is a summary chart to position the hydrogen-powered aircraft thrust in clean aviation and its contribution to climate-neutral aviation. It was already mentioned before that the hydrogen is one of the free thrust, and we'll try to investigate and accelerate some of the technology that could be then used for the for implementation in some aircraft demonstration in the following phase by the end of the program, and it's perfectly matching the EU Green Deal ambitions of the Commission and the strategic research and the innovation agenda that was built with our stakeholders and members. So the main goals are to mature a series of key technologies, matching requirement for carbon-free short-range hydrogen-fueled aircraft. We're talking here about to investigate a completely new path to contribute and introduce into the aviation sector aircraft that will not produce CO2 at all at the end. We're going to demonstrate the potential of hydrogen as a fuel-efficient and reliable and safe alternative energy compared to the current energy means. But we want also to introduce to use a step-by-step approach. So during the first phase of the project, I will try to explain how this step-by-step approach will happen, because it will be a lot of effort in order to select the most promising technology, but also a lot of interaction and within the clean aviation and also with other synergies that we can actuate. And then the target is to achieve a series of key ground demonstration by 2026. By the end of the first phase of clean aviation. Here, I would start to mention some of the challenges that I had in mind. We can start from the first, and that is the hydrogen potential, as due to the fact that it's in fact a high energy source. But it will, and of course, to contribute to eliminate CO2. But we know that this is the volumetric energy density is a bit of a challenge in order to, in particular, to bring over aircraft the hydrogen and then to, for example, to storage it and to distribute it inside the aircraft. So this is this means that a coordinated effort, a holistic assessment at the beginning of the project will be needed to overcome this big challenge. Also because the most of technologies are starting from not quite high TRL level. So some of the technologies are coming mainly also from other sectors. We mind the energy sector, space application. We have, for example, cryogenics pumps that are working, in space application for a few, for some tenths of seconds. Here we are talking about a different environment. So a big challenge. Another challenge is we are really focusing to liquid hydrogen solutions as a primary goal. There is also other options that will be studied in parallel, but liquid hydrogen is the first objective. And then I'm a propulsion engineer, so it's of course to burn fuel, to burn hydrogen will be a challenge. But we have also fuel cell technology. So another important part of the hydrogen trust is fuel cell technologies, where it will be needed a huge effort to scale up the current technology level on small aircraft. We all know about all these activities done currently through the world. But here we are aimed to deliver a multi-megawatt solution as a power plant for novel aircraft in the regional and short-range domain. Also, the colleagues told you about EASA engagement. Of course, also for hydrogen, it will be the same. With our partners, basically our partner, they will engage EASA, and we're trying to follow up because the discussion, because this is of course a complete new field from this perspective. Very important because of course safety requirements and also to try to achieve a permit to fly for the proposed options at the end of phase 1. Yeah, so this is kind of introduction about the challenges. I talk about the synergies as well, so I don't want to repeat myself. This is a bit dense chart, but just to help you to summarize, from the left, you have the strategic research and innovation agenda roadmap. It was quite high level, but already depicting the target. So. A big focus over the end of first phase, in phase 1. In the middle, we have the roadmap. I don't ask you to read, but of course this is available in our work program. And the roadmap is the bit you see on the left is phase 1, 2025. On the right in gray is phase 2, 26 till the end of the program. And you see how dense is this roadmap and how much of opportunities we have, how much links, and in order to deliver the objectives of phase 1 that you see on the right are is a series, of course, of ground demonstrations. So we'll have a ground demonstrator on proving the hydrogen direct combustion. So we will have teams that will work on using, for example, donor engines already so turbofans or turboshafts that are already available, but adapting them to run on hydrogen, together with all the challenges of the related to the systems, the aircraft systems, basically, of course, the one related to engines, so fuel systems, but also for example, fuel system at the aircraft side, and also to be able also to challenge to study also the cryogenic systems, distribution systems, the conditioning of hydrogen to have the hydrogen at the right physical conditions at the injectors in a combustion in gaseous form. So it will be a huge effort to do that. So we will have projects on that. They are targeted to provide. Yes, I will tell you later, because later I will show you one slide for each of these projects. So this is just to introduce the matter. The second is storage system development. So there is another activity line that is aimed to liquid hydrogen storage system development. The third line is a fuel cell propulsion system development, always for short-range application. where the fuel cell could use, of course, first of all, need to be scaled up compared to the current technology level of fuel cell, but then they need also to be developed in a way that they will be part, of course, of a propulsion system, and of course, yes, the so-called end-to-end fuel cell. The last line is aimed to small aircraft, fuel cell powertrains. So we call near-term technology because, of course, there could be maybe the first. It would be the closest technology that we can put into the market, but it would be also some relation to the short-range focus at the end project. In call one, we launched 4 topics. 182 million euros. That represents 25% of the volume of call one. We will fund up to 7 projects coming up from the evaluation that is currently in the final stage. This chart is reminding that hydrogen-powered aircraft is really connected to the other 2 thrusts that the colleague has presented before, so the short, medium range, and the hybrid electric. So the 3 main areas, of course, is direct burn, storage and distribution, and fuel cell propulsion systems. What you see in the blue box at the bottom is the range and payload is the objective using hydrogen, because of course. So, for example, the 2,000 nautical miles and 200 pax, and the 1,000 nautical miles and 100 pax for a regional. This is quite, of course, you may understand, a very demanding objective. So, unfortunately, in this case, the program is not so much leveraging Clean Sky 2 technology because is a new challenge for clean aviation. So we can use only partly of Clean Sky 2 technology. So we're trying to do the best. But and this is really related also to the transversal activity at the bottom in the black box. You have the so-called transverse activity that were mentioned already by colleagues that are the aircraft architecture and technology integration and the new certification methods, where in particular in the first one, the architecture and technology integration, the airframers will define the aircraft concept, taking into account, as Maria said before, also possible concepts that could use hydrogen compared to the technologies that will be proposed for the project in hydrogen, and also the maturity of this project and of this proposal, and the implementation also of the project in the first phases, in order to continue to perform a gap analysis that will allow the project to contribute at the end to reach and exploit the maximum from the hydrogen thrust. Here I would like to present you the call one topic. This is a summary slide. There will be a few slides just after for each of these topics. So as said, yes, we have a big topic. The first is direct combustion of hydrogen in aero engines. It's a topic with 115 million funding. Willing to fund up to 2 proposals. Then there is the multi-megawatt fuel cell propulsion system for hydrogen-powered aircraft, and this is 50 million funding, and 2 proposals. And the third one is storage. It's dedicated to storage, so it's large-scale, lightweight, liquid hydrogen integrated integral storage solutions, 10 million, and 1 proposal. And the last one, as said before, is the near-term disruptive technologies for hydrogen-powered aircraft. That is the project addressing hydrogen implementation into small aircraft, and it's 7 million euros and up to 2 projects funded. This is a chart a bit dense, but just to provide you a summary of what it was put in the topic to answer and to support the roadmap and the work plan of clean aviation. So for the first topic, direct combustion, the objectives is to achieve TRL5 at combustion system level, and TRL4 at the end at overall engine and propulsion system level. So this is the objective by 2025, 2026, beginning 2026 at the latest. And the target is an engine, a turbofan in the class of 20 kilopounds, and or a turbo shaft in the class of 5,000 ship horsepower. The expected outcome, it's of course a first ground test of a propulsion system. And also the big goal is to try to progress into the permit to fly by the end of phase one. Of course, is expected to be done more at the engine side, but also progressing a bit in terms of to prepare a possible flight demonstration for the end-to-end concept, from including the aircraft fuel system. So we are expecting to do also simulation and progress into the development of components and systems for the aircraft fuel systems as well, and it's not only the engine one. Of course, at the beginning of the project, we are expecting that as soon as the first the design will be performed, the preliminary design. A lot of activity will be done using state available technologies. I mean components, so pumping systems, storage systems, metering systems, conditioning systems that are currently available, and then after a first run of test at component system level to go and go further into the definition of components that would be more coherent and in line with the ambition of the airframers. So I would not say more on this, just not to be too long. The objective is of course is in line with clean aviation to mature systems, hydrogen systems for by the end of the program. Of course, targeting some entry into service by 2035. The second topic is the one addressing multi-megawatt fuel cell propulsion systems. Yes, this is also a big challenge. The entry level of TRL is TRL3 at subsystem component level, and the target is similar to the previous one, is the TRL4. We're talking about to scale up fuel cell power system at the multi-megawatt level, and leveraging all the experience that is already available, plus also the synergies, as mentioned also before, with for example, clean hydrogen joint undertaking that is bringing up and accelerating technologies at component level for a fuel cell. Again, here we have the challenge as well of the storage of the hydrogen. We will have the challenge of the distribution of the hydrogen. We are looking also some kind of common solution, just to have quite common, not so different approaches in the for example in direct burn in the fuel cell to develop then at the end a solution that could serve a bit both the purposes with some adaptation, of course. There will be also activity on the electrical systems, and of course at thermal management level, in order to first of all to be able to set a system that will work, but then it will be also used in a more transversal way to we call the is abating the ATA barrier of the system design, in order to find some way to optimize at the end the design of the systems. The target is a 50 pax in this case for this kind of project, and we are talking about purely electrical drive. So electrical motors on wing combined with liquid hydrogen fuel cell. The third one is the liquid hydrogen integral storage. Is a separate topic, but it is really integrated with the previous two. We decided to launch a separate topic to allow the partners to provide the most of the innovation and ideas into finding also some common solutions. The objective is still TRL5 at tank system level, and the objective is to adapt this technology for phase 2 when we will fly demonstrator in line with the other two thrust. So also a big challenge here. For example, we are looking to integrate the tank solution into the airframe structure, for example. So there is a lot of interaction with the airframer as well to find the optimal solution to save weight and to provide a more integrated approach. The last one is the near-term disruptive technology for small aircraft. Again, here we are intending to progress from TRL3 to TRL5 at the end of the project, and the partners will work on an integrated propulsion system at TRL5. In this case, we are talking about 500 kilowatt power systems based on fuel cell. And yes, there is also a part of the project that will also deal with tank research in the order of 100 kilograms. So this is more for small aircrafts, but could provide also a small project, but could provide a good value in terms of solutions. That could be also later on scaled up to a higher level. I jump here to conclusions. The hydrogen is, of course, considered a very promising opportunity to enable for emission reductions in the aviation sectors. It's very interesting because it will involve propulsion systems. It will involve a lot of aircraft design interaction. It will involve also certification that is starting basically from clean sheet at this moment. So everything needs to be developed. The call one will support, of course, ground demonstrators by 2025, early 2026, to be further exploited, targeting a possible entry into service of aircraft in 2035. Close cooperation with the other trust was said. EASA involvement from the early phases, so we are willing to see in the proposal that was received this engagement that is, of course, willing to be done by the partners. And then we will have still the next calls. So next calls that could involve potential partners will be defined soon, and will be launched in the near future. We hope that this hydrogen solution will be good enough to from phase 1 to enter to proceed in a phase 2 and to be able to scale up the technologies. And then, of course, the close cooperation that is not only with EU national programs, but is with all the potential partners that could be interested in this challenge. So this is all for my side. If you have any questions, and
thank you, Paolo.
Thank you very much.
So the final round of comments and questions. There is one up there, please. Yes.
Yeah, Fabrizio Nicolosi from University of Naples. My question is more, let's say, not really technically oriented, but more general. We are facing this new disruptive period in the next 10 years where especially propulsion will be the driver for new configuration or new aircraft, new product. And my question is, especially for all the engine manufacturer, of course, we have also for hydrogen other specialization like the tank. And but concerning the propulsion side, do you think that all the engine manufacturers should really collaborate and work together to plan a common product? Because nowadays we have different engine. Not too many, we have 4 or 5 in the Western world, but in the next period, this will be really challenging. So the amount of money and the amount of investment and the risk that they have to face is really high. So do you think that they should group together, and how Clean Aviation or the board or government can push this? And connect to this question, there is also the parallel question. What about US cooperation? I mean, is really worth that Europe is doing this kind of work, and parallelly maybe in US there are other research programs addressing the same topic? Or maybe we should think about maybe like for Switzerland, for example, they participate to European programs, but they are funded by the government. So,
yeah. So I may say that the cooperations are. So we had examples of cooperations when a new engine version was introduced into the market. Maybe yes, I have some case in the US when GE and Pratt & Whitney pulled together to develop new engines. So of course the hydrogen challenge is quite big. So we can envisage that in the next future something like collaboration like you are mentioning will happen. But we are looking now in Clean Aviation to develop the base in a way that this will happen. So first of all we need to proceed. We are at the early stage now. In few years, we will have a better understanding of what will be the market scenario. So this is something that yes, I think that we cannot say now. But of course, yes, Clean Aviation is offering a perfect environment to be part of this job. And this challenge, but I cannot envisage now how our collaboration could be done, because it is more entering into commercial framework. For example, for engines, yes, I think that we know that the combustor is the combustion system is the key in this case. One of the limitations, for example, of this first project is the fact that the donor engines that will be offered to perform the initial trials on hydrogen combustion are conventional engines, and we know that for example, there is space in future if hydrogen will work also to have the possibility to optimize the design of the combustor, because yes, one of the expectation is to even reduce the length of the module, profiting from the hydrogen combustion that could happen it could allow shorter combustion. This will be seen in maybe in the second phase, but also for other modules at engine level, we can envisage also some optimization. So it is only the case for potential engine makers to follow the evolution, to follow the evolution of the project, and then to understand which could be the opportunities for their own business.
Okay. Are there other comments, questions? Yeah, there's one here in the first. Oh, there's one lady over there. Yeah.
Go ahead first.
So my name is Ramon Lopez. I work at Safran. Regarding this disruptive, coming back to the disruptive designs, if we go, for instance, for a blended wing body configuration or some very novel configuration, there will be also challenges, let's say, in the integration at the aerodrome side as well, right? Because if you have a very odd configuration, which you cannot use the current, like the fingers and the current conditions of the airports, then that will, in the end, also impact the climate, because you have to maybe disassemble a whole aerodrome or change it so much that in the end, all this manufacturing for the new airports, which also the integration of new aircraft will not happen suddenly, so you'll need to be changing only partially, because you cannot just change 100% because there'll be old aircraft anyway. So how is this, has this been thought about? Or?
So I think that what you are saying, what already I remember that was said when the A380 entered into service, all this discussion about the airport infrastructure. Of course, this is an element of to be taken into account, and I think that airframers are very yes, of course, interested to challenge this. We are, I think, at the you saw the blended wing, because I put in the topic description for direct burn. Yes, this is one of the configuration that could you know, is one of the, for example, of the free Airbus 0E configuration. Potentially all the three, of course, will use hydrogen. We have short range, turboprop, and then we have also the blended wing body. So we will see. We are not in the position now to no, because we are still at the beginning, as said. But of course, the airframer with airlines and airport could start a discussion. The other important element is, for example, the liquid, and of course, the hydrogen production. When we are talking about yes, and then also so this is also, as we are speaking about infrastructures, this is also the other important challenge. So to be able that hydrogen will be available, it will be available in the right conditions at the airport on time, and yes, and all the matters related to that.
We are running out of time. I think this is a topic matter for a discussion during the coffee break. But I would like to give the lady over there a chance for a brief question and an even briefer answer, please.
Okay, good.
Sure, this is Gaudi from NASA. So it's less of a question than a comment. I view the challenges with hydrogen at the interface. So it's the interface from the storage to the actual delivery to the engine, if you're going straight to a hydrogen-based engine configuration. If it's fuel cells, it's that interface to the fuel cells, then integrating the whole system to the airplane. So if your target market is regional, and that's really what you're looking for, it seems to me that you would want to take these 5 topic areas and have a common architecture that you're working towards, so that you can make the trades and have the Pareto front of options, because you may choose a different storage mechanism if you have a different cargo or payload capability. If you're truly going straight to a hydrogen engine, that may also change the way that you store it or the way that you deliver it. So it's just a comment that in doing this work, which is excellent roadmap to maturing the systems, a common architecture point that everyone has to address and define the requirement space would be really appropriate.
Yes, thank you. Then
thank you. So it
was a nice statement at the end. Thank you very much. Thanks, Paolo, and thanks to all of you for attending this session this afternoon. We are now going into a 30-minute break, and then afterwards at 4 we have the von Karman Award, just for you to be aware. Happy to see you then again at 4 o'clock in this room. Thank you very much, and have a good afternoon.